So, right, thank you so much for coming to my talk. Having your attention is an honour, absolute honour, and I really appreciate you taking the time out of your day to listen to me prattle on about containers. How many of you have too many containers? No, probably not all of you, but many of you will eventually, because believe me, this is the thing that's going to sweep everything away and change the game for all of us. So one day you will all have too many containers, if you don't have today. So once you do have lots of containers, what do you do? And really, it doesn't have to be having lots of containers today. This kind of stuff we're going to talk about is applicable anyway. And feel free to use the tool to ask questions. You can also tweet me about anything you like throughout the day. I had to run off because of Twickenham. I lived that way, and apparently it's going to be an absolute disaster this afternoon. So I'm going to run off by about 2 o'clock. But I'll be there for lunch. If you want to chat, talk about Kubernetes or Google Cloud or anything else, not Android though. I don't work on Android. Feel free, and I'll be there. So yeah, tweet questions, anything. Hashtag GOTO London, so please tweet about the event and make it successful, because this is a really cool event and we should promote it as much as possible. So, what's this? And I'm learning Japanese, so I did this talk in Tokyo recently. Kore wa nan desu ka? And it's pretty much all I can say in talks. I know quite a lot of Japanese, but I'm not very good at speaking it yet. So I'll keep on trying. But what is this? This is a data center, a Google data center. It's in Council Bluffs, Iowa, wherever that is, somewhere in the Midwest in the US. And this is what we call a cluster of machines. And there's lots of machines. And if I left it up for a long time, you might be able to count them all one by one. But this is what our software engineers, our developers use to run their stuff. So how do they run their stuff? What do? Do they kind of select a machine in a rack in a data center and say, let's FTP into that, send my binary over, SSH into it, stand up my binary, maybe do that many times across a whole number of machines? No, they don't, because that's not going to work, right? Just absolutely no way they can do that. It's not the best option. So what do? So what they do is this. They create a configuration file called a Borg config. We'll talk about Borg more shortly. The configuration file has a name. In this case, it's a job. And it's called Hello World. So this is Hello World for the data center. And they can say what cell they want to run it in. And a cell is a subdivision of a cluster. It's 10,000 machines, say, on which they can run their stuff. So they're saying, I want to run it on this cell. So the cell is the target, not a machine. They can say what their binary is, and the binary would be a statically linked binary. Remember those? They're coming back. They're coming back. All of that dynamic linking is going to go away. So statically linked, and it includes the web server in this case. This is Hello World. It has its web server embedded in it. It carries it around with it. So we can just move this around and run it anywhere. We don't have to worry about what's on the machine. It will just run. Ultimately, it'll run inside a container. We have very lightweight containers at Google, and we've been using them for a long time. And that's one of the reasons why we worked with Linux to implement C groups and namespaces, which we're not going to talk about too much today, but I'm happy to answer questions. And so this is the binary. We have that. Arguments as well. This is a web server. We need a port. Requirements, resource requirements. Oh, this is interesting. Okay, how much RAM does it need? What do we think it needs? How much disk does it need? How much CPU does it need? 0.1 of a CPU. That's pretty good. And we can also say how many copies of it we want to run. We want 5, maybe. Although this is Google scale, so maybe 10,000. 10,000 is pretty good, right? So let's run 10,000 of these things. And me as an engineer working at Google, I could do this. I don't need any special privileges. I can go off and run this thing, and nobody will complain. Nobody can say, what are you doing running 10,000 Hello Worlds? Because that's fine, apparently. So that's what we do. It's all declarative. We create the binary. Obviously, we have a build system. The build system is now available externally, called Bazel on GitHub. So if you want access to our distributed parallel build system, that's available as well. And why am I telling you all this? I'll tell you why I'm telling you all this in a minute. The developer view of this. So after 2 minutes 40 seconds, we ramp up and we do ramp up. We don't try to start them all at once because it doesn't make sense to do that. The binary is 50 megabytes in size, so we have like 2 gigabits per second of data to move around. Lots of caching going on, but we have to ramp this up reasonably slowly. So that's all part of the system. Ramp up, 2 minutes 40 seconds. We have 10,000 of these, or so. Maybe not quite 10,000. I'm not going to go into details of that, but there's another talk online where I do, and there's various reasons why we may not reach 10,000, but that's because of the sheer number we're running. But I can tell more about that as well if you need to know more. So what just happened? This is a typical cell, what the cell looks like. Borg is our scheduler, is our cluster scheduler. It schedules our containers for us. So this is the thing that replaces the guy having to SFTP into a machine and stand up a binary, or GEL, I should say, sorry. And what we have here is a Borg master. This is the thing that controls everything in the cell. And it's highly replicated, it's very resilient, 5 copies. And we have lots of machines down here. These are the nodes, or the machines in a rack that you saw earlier, right? So these all run in a thing called a Borglet. So what happens is this. The developer compiles the binary, and it gets pushed out to some centralized store for the cell level storage. And then they create the configuration file, and they run a command, Borg CFG on the command line, and push that configuration file out to the Borg master. This goes into a persistent store. This is Paxos-based, consensus-based, and we're using Paxos. We haven't got called on Raft yet. So I'm not going to get into a kind of religious debate about that either, though. But. And then we have now a state of the system. This is what it is currently, and there's what we want it to be. So we've just now said we want 10,000 of these. And the scheduler comes along and says, what's the state of the system? Compare it against the state of what it should be. I should have 10,000 of these running. They're not running. I'll fix that. So it goes off and fixes it. It creates a plan. Then it talks to each of the machines that it's chosen to run this job and says, please run this for me. The machine will go and get the binary from storage, and it will run that. And then ultimately we have that. We have lots of hello worlds. Right, okay. So why is that relevant? Because basically Kubernetes, which is what we're talking about today, is our attempts to give everybody that kind of thing, allow everybody to do exactly what we do internally within Google. Because this is the way we're going to do these things in the future. This is the way it's going to be. Things will change. Those machines that we had before, they're going to go away. You know, we're going to have clusters of machines, and we're going to be running cluster schedulers, things that will intelligently run our stuff for us somewhere, and we don't know where. Or at least not exactly. It's a bit like Heisenberg's uncertainty principle. We know how big it is, but we don't know where it is. And so we're going to use a typical application for this, a very typical Lampy type. Is there such a thing as a Lampy stack? So it's a Lampy stack that has PHP, many PHP front ends, MySQL, which we'll cover later. How do we do this with containers? Traditional Memcache, and we have a client consuming, or clients consuming those services exposed by the PHP application. By the way, I haven't got a slide introducing me. I'm Mandy Waite. I'm a developer advocate. I normally have a slide, I left it out. I'm a developer advocate for Google, and I work on cloud exclusively. If you want me to talk to me, GOTO London slipped off. GOTO London should be on all my slides. Sorry, Nikki. GOTOLDN, hash. It's a hashtag. So you can get me on @TechGirl. If you want to talk about Kubernetes generally, #Kubernetes. Okay, so let's talk about containers. How many of you are familiar with containers, Docker specifically? How many of you have spun up your own container, actually created a container? Many of you, okay. I'm going to run through this very quickly, just for the benefit of people who aren't as familiar, but I won't spend too much time on what containers are. So this is the old way we used to do things. We used to have a machine next to our desk, and it moved into a server room. We probably had a name for it. We could probably log into Grond, which is my machine's name is called Grond. And if anybody knows what the reference is, please let me know, because Lord of the Rings. So shared machines, we would run everything on the machine. We'd stand up the machine, run this stuff. And the green app, the green application in this case may be our really important business critical application. And the red one may be something really silly. and the red one may one day go completely mad and consume all of our CPU and all of our memory and take the machine down and take down our production machine, our production services completely. No isolation. We can't guarantee that one application won't break another. There's no namespacing. They all have exactly the same view of what the system looks like. There are no common libraries. Well, sorry, that's not what I meant to say. There are common libraries. These libraries are shared. So with dynamic linking, pretty good, works pretty well, but sometimes you may find that you may update an application or install a new one, and something changes your libraries and may break something for something else that has a specific dependency on a library. It doesn't happen very often. If it's well written, it shouldn't happen, but it does happen occasionally. And ultimately, the applications are highly coupled to the operating system. So then we have virtual machines. We have basically now introduced a hypervisor, a layer of idealized hardware on top of the actual hardware. So it looks like hardware, it's not really hardware. But to operating systems running on that system, it looks like a piece of hardware. Idealized hardware, the hypervisor. And now we can run individual virtual machines for every single app if we wanted to. So we could have one machine for the red app, one machine for the green app, and they won't impact each other now when something breaks. There's some possibility that it could happen, but very unlikely. But if anybody's had to manage a large number of virtual machines, you know that that's quite difficult as well. You have to actually install these things, configure them, just like you would at any kind of normal machine. Also, the application is still highly coupled to the guest OS, and this whole setup scenario can be hard to manage. The new way is containers, and now we move up the stack. We take this idealized piece of hardware, we move up a level, and now we have an idealized operating system on which we can run things. And those things that we run are containers, often Docker containers. In the future, there will be standards around containers. We will have many different container formats, but hopefully there will be an Open Container Initiative standard container format that they will all comply to. They will add value. Docker will add value. CoreOS will add value with Rocket, etc. And so containers are the new thing, and they're great. I wanted to just quickly mention this as well, because we're going to talk about volumes shortly. Containers, Docker containers specifically, are created from images, and the images are built up in layers. So we have read-only layers upon layer, and we have a read-write layer at the top, which is our application. So that's how it's all built up. In this case, we have Debian, we have libraries, we have PHP and Apache, then we have our application code sitting on top of it. And this is all copy and write at the top layer. So the whole process will be to build an image, push it to a repository, and this could be hub.docker.com or hub.docker.io as it's called now. And it could also be some private repository, something that's specific to you. Then you'll pull it back to the execution host, which could be different from the machine you built it on. Then you'll start the container from that image. That's how the whole process works. And images have layers, as I said. I'm not going to go into too much detail. I was going to, but I'm kind of worried about the time. So let's move on. And ultimately, we can mount a host directory as well. And this is important when we get to databases shortly. So it's possible to mount a host directory into the container's file system, its view of its own file system. And these are completely mutable. They don't outlive the container. And they're only available on one specific host, on the actual host you mount them on. You can move them around and they can mount a different directory, maybe the same path, but it will actually be a different directory. So there's a possibility that the state of one container run on one machine may be different from the state of a container run on another. Important note. Then we have a Docker example. So Docker is the canonical container format that everybody's using, and it's pretty impressive. I saw Solomon Hykes talk 2 years ago at .scale in Paris, and it was extremely impressive the way he compared it to shipping containers. So if you've heard that analogy, it works so well. And here, so we have some containers. We have our application code running on top of PHP and Apache. We have memcached, and we have MySQL. For the PHP and Apache and memcache case, we have those layers. Some of those layers are common. In this case, the library, the lower level libraries are common between both. But they also have their own libraries, and MySQL is completely separate. It has all of its own dependencies. Beneath that, we have some operating system, and we have a server. which could be a bare metal server, it could be a virtual machine, it could be your laptop, it could be pretty much anything you can run Docker on. The Docker engine is the runtime effectively for containers, and it's the thing that manages running the containers and also manages the processes of creating them. The Docker command pretty much does all things, and that's kind of crazy. So why containers? I'll go through this quite a lot, but basically containers are awesome, so just let's use lots of them, right? That's the best thing to say. We can go back to that, but you know this probably. Okay, so performance, they're quick to create. Once you pull down an image and cache it locally, they're very quick to spin up. They offer repeatability, so whenever you create an image, you can pretty much guarantee that every time you run that image, it will be the same. Quality of service, you have resource isolation. You can allocate resources. Like we saw the Google engineer earlier, she would allocate X amount of memory, X amount of CPU, or would at least request that. So we can specify quality of service for these things when they're running. Accounting is very easy. These things are small, easy to spin up, and easy to manage, and easy to track. Portability is probably the most important part. You can move these things from one machine to another, from a laptop, from a testing server to a production server. So all the way from dev to prod, test to prod. And that's a very important use case for Docker containers today. But one day, everything will be in a container, believe me, really. I mean, everybody at Google now is, I'll spin up a container with it. You know, I'll put Chrome into a container, you know, because then I can stop it from eating all my memory, which is pretty cool. I love Chrome. This is a fundamentally different way of managing applications, and it's going to change your life. And I've said this to people many times now, that in a couple of years' time, I'll talk somewhere, if I'm still able to, and you'll say to me, Mandy, you told me about Kubernetes 2 years ago, and you were right, it's changed my life. Everything's different. I no longer have a job. No, you won't say that, hopefully. You'll say, I do have a job because Mandy told me about Kubernetes really early on, and I got on the bandwagon really quickly. So containers are awesome, let's use lots of them. A demo. I was going to do a demo. Am I going to do a demo? Yeah, okay. So I'm cheating because I'm using my history, but my typing is absolutely appalling, and it would take me like half an hour just to write this one command. So what we're going to do here is use a command called kubectl, and this is going to allow us to actually deploy a container to Kubernetes. And we'll talk more about Kubernetes shortly. We're going to use a Docker image. So the Docker image is here, memcached version 1.4. We're going to specify a port, and we're going to specify some labels. And we'll talk about labels shortly. And I have here, if it's still running, which is not, it's stopped. Internal server error, no. We have a proxy, basically, with a web UI that is talking to the Kubernetes API and not resizing the window, which is kind of weird. Okay, do that then. And if I run this now, we should see a container. So this is memcache. It's yellow currently, which means it's pending, and it has what we call a replication controller. We'll talk about these more shortly. One day, I'm going to get rid of all my slides, and I'm just going to use this to go through my entire talk. I'm not quite there yet with it. So we have a container, which is a grey one, and we have this thing called a replication controller. And we could potentially, and I have to make this command up as I go, expose that as a service. And we're going to get into services as well shortly, but we can do this. And that will create a service for us and effectively allow us to access memcache through this shim layer called a service. And we'll talk about that more shortly. But now we have a whole configuration. We have an endpoint with an IP address, we have memcache running, and we have something to actually manage our memcache processes. So let's go, oh, I'm going to delete that because I know it's going to break later if I don't. So I'm going to do kubectl get rc. Oh, it's all memcache, it's unsurprising. And kubectl stop rc memcache d. I keep dropping the d at the end. Right, so they should be gone now. And, oh, the service isn't gone. Of course it isn't. And that's also called memcached. Oh, services. I always forget that. seems logical just to say delete memcached. Right, okay. I did that today. It's probably a bit mysterious, so let's talk about Kubernetes. And let's do some live editing of slides. You should really create your slides while you're giving your talk. I think that's really the best way forward. It's just so much more interesting doing it that way. Right, and the Wi-Fi's working great, isn't it? It's really cool. We don't notice it. We don't say when it's working great. We go to conferences, it never works. And we swear and we tweet and we say horrible things. But when it works brilliantly, we don't say anything. It's working brilliantly today. So Kubernetes. How many of you have heard of Kubernetes? Okay, right. How many of you actually want to know more about it? Or just already know so much about it that you don't care anymore? Right, so Kubernetes is something that, it's an open source project basically that we launched last year. And which is open to everybody and has lots of contributors and committers from all over the place, from Microsoft, from Amazon, from CoreOS, from Mesosphere, from Red Hat. Everybody's contributing to this thing. So it's not just Google. It's a real, we're not like a single contributor kind of model for an open source project. And the word itself, how many of you know how to say Kubernetes? Because I'm quite happy to stand outside later and help you say it properly. It's harder to do with other people. Japanese find this really easy because it's made of Japanese syllables. So Kubernetes is effectively an orchestrator or a scheduler for Docker containers. And it supports multiple cloud environments. It will run on Amazon, it runs on Microsoft Azure, it runs on Google Cloud, it runs on top of Mesosphere. Red Hat use it for OpenShift, and there's many, many different use cases. And there's lots of new stuff coming along in the pipeline. You're going to be quite amazed how many people are going to be using Kubernetes. This is inspired and informed by everything we saw earlier. All of that stuff I showed you earlier actually had a point. Because basically we've learned through our Borg scheduler how to build a cluster scheduler or a container scheduler. And we think Kubernetes is ultimately going to be better than what we built with Borg because we have technical debt, everybody has technical debt, and there are things we would change about Borg if we could go back in time, but we can't really change them now. So now we're going to be introducing Kubernetes, and while it doesn't do everything that Borg does today, it will do eventually. It's open source, written in Go, and it's basically there for managing applications, not machines. Forget about machines. We don't care about machines anymore. Concepts. We're going to go through these one by one, but we have containers, pods, services, volumes, nodes, replication controllers, and labels. Wow, that's a lot. That's quite sad, really, but we'll try to do our best to explain them. So developer view, Kubernetes. This is what we saw with Borg earlier. It's very similar. We use the same colors, at least. And we have a Kubernetes master. Kubernetes master is there to schedule our containers for us. It has a scheduler component. It has this thing called a replication controller. It has an API. The API is brilliant. That's what we're using for the visualization. The API is used by all of the external tools, a thing called kubectl, the command we ran, the proxy that we're using to do the web UI. Your application will use this as well. We have a kube user interface which shows you the utilization of your nodes in your cluster, where your pods are running, which is connected to via web browsers. And we have nodes. Nodes very similar. They don't run Borglets, they run kubelets. And we also have a thing called a container registry. So this is like our cluster, our cell level storage. This is where we push images to. And we could push them to Docker, we could push them to our own private container registry in the cloud. And we have the ability to run this stuff, Kubernetes, on a laptop using VirtualBox. We can build a highly available multi-node cluster. This can be hosted. So we provide a hosted version of Kubernetes called Google Container Engine. Or you can manage it yourself. It could be running on your on-premise services, your on-premise servers. So if you have like 100 servers lying around doing nothing because you moved everything to the cloud, you could just run Kubernetes on it, and it would be really, really good use for them. You can run it in the cloud, on bare metal, virtual machines, and there's many, many different options. And you can see those options in the matrix there. So if anybody doesn't have time to get that link, I'm happy to point you to it later. So what do we run on the nodes, containers? That's when it should have done the demo, now. So that demo I did earlier was this demo here. But I added that on the train this morning. So pods, let's talk about pods. So what we saw earlier, we ran a container. We said, this is the image, I want you to run a container for me. But what it actually did was create a pod. A pod is the atom of scheduling for containers on Kubernetes. So when we schedule anything, it will be in a pod. And we could have a container in a pod, one container, or we could have two containers in a pod, like peas in a pod, or we could have more than two, where it makes sense to. And think of these pods as being like logical hosts. When you used to install a machine with Apache and maybe with a CMS, something like Sinatra or Jekyll, when it makes sense to run them side by side, then that makes sense to run them in a pod, where they live and die together, where one doesn't make sense without the other. So when you can pull the plug on this one, it goes away. You haven't got some container that's no longer doing anything running. So where it makes sense to run them together, you put them in a pod. These are ephemeral, they can die and they can be replaced. No state. They don't contain state. They contain temporary state, but they shouldn't contain important state, business critical state. And we've already seen that a single container pod can be created directly from a container image. And so here's an example of how we would couple them together, how we'd have a logical host running a Node.js application and also something that synchronizes with Git. So this is a typical push to deploy scenario where your developers will push something out to Git, maybe to GitHub, and you have something running in the container that's saying, I'm looking at this Git repository or this GitHub repository, and whenever I see any changes, I'm going to pull those changes down, store them on a volume within the pod. We'll talk about volume shortly. And the Node.js application will now pick up those changes and start serving those changes. So it's push to deploy, effectively. You deploy your changes to Git, and they automatically get deployed to your running application. So continuous deployment almost. Containers are tightly coupled. They live and die together. They have a shared network IP and ports namespace. Local host is the same to them, so they can talk to each other on ports. It looks like they're running on a logical host, effectively. So think in terms of services that you would usually run on the same machine. And if you have any questions about pods, let me know. I used to have more slides, but I've cut back on them because too many pod slides, bad. So we talked about volumes. We have different kinds of volumes, and these allow effectively individual containers to write data. They like to write to file systems, or for multiple containers to share data between them. And in this case, we have two containers. The symbol, the gear wheel is a pod symbol, and a volume. And what they're actually backed by, this volume is backed by, is determined by the volume type. And the first one is an empty directory. And this is basically backed by persistent storage on the disk, but only temporarily, effectively. So it lives while the pod's alive and goes away when the pod goes away. So this is for pods sharing data, temporary data between them. It doesn't persist after the pod goes away. So empty dir is useful for having that kind of transient data you don't really care about. Second one is mapping to a host path. You can map to a directory on the system, the node on which the pod is running. And that's quite useful, but again, it's a little bit dangerous because what it's mapping to may be different on one machine than it's on the other. It may have different data, it may have different conditions. Probably not, but it's an important consideration. And the next one is a volume and a volume, well, not a volume, NFS volume or GlusterFS, we can mount that. And also we can do cloud provider block storage. So for Google, we have Google Persistent Disk, and Amazon has AWS block storage. Labels are the single grouping mechanism within Kubernetes. In this case, we have type equals FE. So this is arbitrary metadata that's important to you, but not to Kubernetes. So key value pair, type equals FE is a label. And you can build dashboard applications that can select on a label. Give me all the pods named this. Give me all the replication controllers with this label. And you can build your own dashboards. Or you can build another dashboard that looks at a different label. So in this case, we have two dashboards, two different labels. Each one's looking at different labels. So you can build your own tooling around this. And then there's a developer view, which is going to run through very quickly, which is very similar to what we saw before. We can specify resource limits in terms of CPU, in terms of memory, container mappings, and how many copies we want. So in this case, we want 10,000 replicas, 10,000 of those pods running. Replication controllers are there basically to keep the pods up and running. So basically, we have this notion of desired state. We say we want to have 2 of these containers running, or 2 of these pods running, which could be multiple containers. And here's my template for building new pods. It could have 2 different container definitions, 3, 1, but this is the template you're going to use to create new ones. And so we create the replication controller and say you're interested in pods with version equals v1. If any exist, it will pick them up. If any don't exist, it will create them up to the number that it's been told to have. In this case, pods equals 2. So we'll have 2 pods, version equals v1 being arbitrary metadata. And we can have another replication controller with version equals v2. In this case, 1 pod. And it will make sure there's always 1 pod in that case. And so this is just an example of a control loop. It will continuously check to make sure that the desired state is what we have. This is what the actual state is, this is what you want it to be, and it will fix it. If there's too many running, takes them away. If there's not enough, it adds them. Container liveness, we can do health check-in. There's some basics. I'm not going to talk about this. The zombie is really cool. They're not green in The Walking Dead, though, are they? Maybe they will be one day, like in season 10 or whatever. Services. Services are the things that sit in front of pods and effectively aggregate them as something that can be consumed by clients. So at the bottom here, we have 3 identical pods. They would all have the same label, and we'll talk about that shortly. When we create a service, we create something that has a virtual IP address and a DNS name, and clients can attach to that. They can be internal clients or they can be external clients. And effectively what the service will do will load balance requests randomly across each one of the pods. It has session affinity, client IP affinity, so there's a session in progress, it can go back to the same pod, but it will load balance randomly across all of the pods. And the constituency of a service, I deleted the other slide, never mind. The constituency of a service is made up of labels. So in this case we have 2 replication controllers, version equals v1 for one of them, version equals 2, v2 for the other. And each of the pods also has a type equals FE label. And our service cares about pods with label type equals FE. So it has a label selector, type equals FE. So all of those pods belong to that service. But notice there are 2 different versions of the pod here. So we could roll out a canary here. We could roll out one pod that's different from all of the others, just to do some kind of A/B testing. So we're getting some of our traffic going to the new version, some of it going to the old version. That has the virtual IP address, and this could be consumed by external clients or internal. So mapping to Kubernetes, that D keeps dropping off down there. Naughty D. This is what it looks like in terms of Kubernetes. We have pods, volumes, services, which is the long rectangle, replication controller down here, and a client which is been exposed as a service for the clients. In terms of state, I'm going to have to run through this because I added this morning. I didn't realize I wouldn't have enough time. So, database, everybody asks about database, and I can talk about this later. In a cluster of ephemeral containers, the application state must live outside of the container, right? It can't be in the container. So how do we solve that? The first one is we can have the database outside of the cluster. So we have all of our pods running applications, in this case 3 different applications, different colors. And the MySQL is effectively managed by a DBA or some kind of managed cloud service. So that's one solution. The other one is to adapt your database to run inside the cluster. So in this case, MySQL will run as a pod, and it will mount a file system when it becomes live. When it fires up, it will mount a file system. And that file system will be provided by the cluster. Or we can do cluster native. And this is things like Cassandra or React, which understand how to run in a distributed system. And these things can just have multiple instances running in pods, and they can talk to each other and communicate with each other. And the way networking works within pods, that's very, very simple to do. Simpler than containers generally. So the real demo. And find my shell window, which is now much bigger than it used to be, right? Or in a different position. You're hiding, where are you? Come here. Naughty shell window. Stop it. Oh man, come on. There it is, look. Hello. Right, so let's go back to our visualization and close the console. So the first thing we're going to do is create a disk. So one thing, it's in Japanese, I'll use this one. One thing we need to do is go into the developers console and create a disk. And we're going to go into compute engine, disks. And then we have to find out what the name of the disk is. And for that I will resort to Atom. And I will look at my configuration file for my container and my pod. And I know I have to mount demo MySQL disk. So I'm going to create that disk, new disk, give it a name. The name is important because it's going to mount it based on the name. I have to put it in the right zone in this case. And sorry, this is kind of advanced Google Cloud stuff. So 500 gigabytes should be enough for our MySQL, effectively. And we can create that. So that's been created. We have a 500 gigabyte disk in the cloud. And that's not attached to any nodes currently. It will be shortly. So the next thing to do is to go away from the Japanese stuff because you don't want to see that. And I'm going to use that kubectl command again. -f. Ooh. MySQL server. And that will create me a service and a pod. The pod is MySQL. We have namespace in here. We won't talk about namespacing today. It's yellow currently. It's penned in. Hopefully it's going to mount the disk and everything will be okay. If not, I have to recreate it because I did something wrong. But hopefully I didn't do anything wrong. So in the meantime, we'll create, oh yeah, it's working. So it's now running. So we have MySQL running very quickly, right? That's probably the quickest we've ever seen MySQL up and running, right? So Memcache is the next one. So Memcache. And this will create a pod and a service just like before. Again, namespacing we don't care that much about. Our next thing to do is create a front end. And the front end will be our PHP stuff. And this is going to be a replication controller. Remember we mentioned those? We create that, and what we'll see is a replication controller, which is the blue box here. We've seen them before. And 2 pods, 2 replicas of our PHP application running. Everything's running now, but we don't have a service for our front end. We have to create that. So next thing we do is do that, and it will create a service for us. So now we have a service, and we can plug that in. So now we can see that the front ends here are talking to Memcached, because they will go to Memcached first. If it's not in Memcached, they'll retrieve it from MySQL and stick it into Memcached. So that's the whole process. The front end needs to be exposed to clients. It has an IP address, but that's a cluster local IP address. So things in the cluster can see it, but nothing else can. But there's a special instruction in the configuration file that allows us to create a load balanced endpoint that will be exposed to clients, depending on the cloud provider. So Google Cloud supports that, and others do as well. So in this case, if you say type equals load balancer, it will say, I need to create an external endpoint. So if it's running on a system that can have such an endpoint, like Google Cloud Platform or Azure maybe? Yeah, I think Azure does as well. You can have it create a load balanced endpoint. That takes a little while, so let's fall back to the slides. And oh no, it's there already. Okay, we'll do that. We'll go on, and I'll click on that. It will take me to this. There's a brand new MySQL setup. My colleague Robert's actually automated this, and I should do it. But we have to run setup to create a table. So now we create tables and a database with MySQL, and then we can run index.html, and we can see container camp. Oh no, it's the wrong one. That's no good, right? So, but secretly we've had our techies actually create one specifically for GOTO London. So, but they haven't rolled it out yet, which is bad. I'll have to tell them off. So I should be able to store something now, and this is always risky. I may have done something wrong, but okay, so I've stored it. So if you access this IP address now, you'll be able to send your own messages, and no rude ones, please. Right, so that's great. We want to update this. One of the magic things about Kubernetes is we can do a very quick update. So let's do the quick update. And we're going to do a rolling update. And I'll move this up rather than clear my screen again. Rolling update, we're going to say what the name of the front end is. And it's RC1, which we can see. We go back to our visualization, which I'll put in a minute. -f is the file, new configuration file, and the update period. 1 second. I better go back to my local host so I can see the viz. So this is the visualization. We're going to do the rolling update. I'll move this down, and we can see the magic happen. So we have one front-end controller, 2 pods. And we want to replace those 2 pods with our new version of our application. And first thing, creates a new front-end controller. It creates a new 2.0 pod. And then it will take one of the 1.0 pods away. And next, it will create another 2.0 pod, as if by magic. And now we have 2 2.0 pods. And now it will take the other 1.0 pod away. We've completely rolled out our update to all of our pods, and this could be 100 pods, many more. And finally, the last thing to do is remove, oh, sorry, I got 3 in that. I didn't change it. It's now got 3 pods because the configuration file had replicas equals 3. And now it removes the old front-end controller. And that's it. So now we should go to our application and see our changes. Fingers crossed. It's exciting. Yay! Awesome, right? And people are trying to do, you come and look, I work for Google. And it's like, you're not going to be able to do it, right? Yeah, we don't let that happen anymore. So that's pretty much done. We'll wrap up now. There's some other things I'd love to show. But there's more of this talk online as well. And I'm changing the talk every time to make sure that people have seen it before, get some new stuff. All of the database stuff is new, and we're going to add more in the future. And I'm going to start talking about this slightly differently, more about use cases as opposed to anything else. The visualization is something like this. We have a proxy running in our cluster, which we can connect to the API via. So the proxy code is all running on my laptop. The Open Container Initiative was introduced at OSCON on July 21st. Basically, everybody's going to agree on the container format. And I expected this to get really bad. There'd be many container formats, and then somebody would say, we have to have a standard, and there'll be a standard, and they'll come back together. But it's happened earlier than I expected. So now we have a standard. So everybody can build containers that comply with that spec. We can run any container on Kubernetes. Kubernetes is open source. We want your help. You can contribute to this thing. Go to kubernetes.io to see the documentation. Go to the GitHub project to sign up as a contributor. Talk to our people, our engineers, and they are seriously on IRC, on #Google-containers. This is not a wasteland. This is kind of a bit of a nightmare, in fact. And tweet us on @Kubernetes.io. And questions? Hey, 2 minutes over.
Can you read this?
Are the master components HA? Right, okay, good question. So, Kubernetes is at 1.0, and it probably went a little bit early to 1.0. It does not have, so the question is that thing, that master thing that we saw earlier, is it highly available? And let's look at that. This thing here, is it highly available? Because we saw 5 copies of that in Borg. Is it highly available? And the question is, no, it's not currently. If you want high availability currently with Kubernetes, you would have to have multiple clusters. Or you can run it on something from a provider, and I'm going to suggest Google Cloud Platform, but you could try others. Google Container Engine, which is our implementation of Kubernetes, hosts your master for you. So we take it away from you. You build your cluster, we take the master away, and we look after it. We feed and water it like a puppy. And you don't have to worry about it anymore. So we are responsible for keeping it running. And we have some tricks and stuff we can do behind the scenes to make sure that is always running, like Gmail and search. So you can pretty much not worry about your master if you're running Google Container Engine. If you're running it on your own machines, you probably should fall back on multiple clusters currently. But this will change. There will be high availability at some point. Who answers the question? Anybody? No, any more questions? No? Any other questions? Hey.
Yeah, that's
oh, let me answer your question first.
So if you have a pod with containers, and how with replication,
yep,
can those pods detect each other, their siblings? So they can connect to each other.
Right, so do the pods know about each other? No, not really. That's not the way they're designed. That would create a complicated n times n interaction, right? So basically things would communicate to the pods via the service. They won't know which pod they're talking about. There's a pets versus cattle analogy, which I really hate. I prefer crops versus flowers. You give your flowers names. So these pods are like crops. We don't care about them. They can come and go and be replaced by something that's equally identical. So they don't know about each other. We can probably set some environment variables to say how many there are, and pass information, but it starts getting sneaky, and you start getting tighter coupling that way. So it's probably best to avoid those kind of scenarios. Provisioning MySQL is very impressive. Have you tried it with enterprise database tech like Oracle or DB2? Let me think about that. No. No, one day I'm pretty sure Oracle will be running on this kind of cluster. I mean, Sun basically invented all this stuff with Solaris containers. Well, I didn't, and BSD jails as well. I used to work for Sun as well, and I left when Oracle purchased us, which I had to. So no, we don't support Oracle or DB2. I think, considering the requirements for access to file system the way it does, I think it would be extremely difficult to have Oracle running on Kubernetes, but maybe one day. Any more questions? Alrighty, so again, I'm hoping that I just kind of inspired you to look at this thing. It's probably a lot of it's too much to take in and all that kind of thing, but you need to look at it and play with it. Tweet me, ask me questions. Find me out there. I'll be drinking tea, and I used to drink coffee, I gave it up there. Drinking tea and talking to people and doing stuff, and I'll be leaving to escape the rugby hordes around 2 o'clock, but I will be here to answer your questions. So thank you for giving me your time of your day. I really appreciate it, and goodbye.